Thank you so much. So thank you for having me here. It's a great pleasure to visit NIU. So today I'm going to tell you something about the space of conformal boundary conditions. It's going to be based on this paper from July in collaboration with Hyun-Soo Ha, Dong-Hyuk Kim. They are students at Princeton. Yuya Kusuki from Japan, Shuei Oyama from Austria, and Shinsei Ryu at Princeton. There was a closely related paper posted on the same day on arXiv by Sueda Wen. It has a very different perspective, but closely related. So if you are interested, please check out both of these papers. So to begin here, let me start by asking maybe a big question. So when you study quantum field theories, oftentimes it's very useful to study QFTs, not in isolation, but as an entire family. Of course, the standard example of this will be, for instance, we study RG flows between different QFTs. We try to map out phase diagram of a given theory when we vary coupling constants, and so on and so forth. So there is some big theory space that you may wonder what it is, how it looks like, what are the disconnected components, and so on and so forth. A slightly restricted version of this question is to study not the space of arbitrary quantum field theories, but the space of conformal field theories, which are related to each other by exactly marginal perturbations. So in the literature, such a space is often referred to as a conformal manifold. So here I put conformal manifold inside quotation marks because even though it's called a manifold, sometimes it's not a smooth manifold globally, and it may have some singularities and so on. In any case, maybe one reason why we call it a manifold is because at least locally it's equipped with a metric, which is computed by two-point function of exactly marginal operators. So here OI, OJ are the exactly marginal operators in your CFT, and then by computing this correlation function with some deformation lambda, you can define a metric called geometrical metric in this space of conformal field theories. So the geometry of this conformal manifold plays a very important role both in string theory and holography. For instance, in string theory, this conformal manifold will correspond to the moduli space of string vectua, and in ADS CFT, conformal manifold of the boundary CFT will be related to the massless particles in the ADS gravity. And today's talk will be about even more restricted version of this question. So I'm going to fix my QFT or conformal field theory in the bulk to be some arbitrary theory Q of interest. And then I'll try to understand something about the space of conformal boundary conditions of this fixed conformal field theory. In particular, yes.
Sorry, so you said it's more restricted, but it's more general because you can take the bulk CFT to be a TQFT. Then of course the usual CFT conformal manifold will be a special case.
Of course. Yeah, that's a good point. So it actually goes both ways, indeed. So it's more restrictive only when I restrict my space-time dimension to be a particular number. Okay. So yeah. So I'm studying one. Okay, I'm gonna study only 1+1D conformal field theories in this talk. So Ifan's comment: if I consider boundary conditions of 2+1D topological field theory, that sort of includes all the 1+1D CFTs, so these problems are of course closely related. Anyways, so I'm gonna study 1+1D CFT. So what I mean by space of conformal boundary conditions. So first, yeah, it's a standard to consider a CFT, say on an infinite half plane. So here, my boundary is along this horizontal line.
Sorry, 1+1 is Euclidean, right? It's not one time, one space.
So yes, so it's not terribly important in this talk which signature I mean, but yes, indeed, mostly I will be in the Euclidean signature. So here, yeah, maybe I should have just said 2D CFT.
Yeah, because otherwise those would be initial conditions, and it would be a set of very restricted initial conditions.
Yeah, good point. So I'm gonna stay mostly in the Euclidean signature, so let me just correct 2D CFT. So okay, so I have a 2D CFT defined on a HEP infinite plane, and I'm gonna import some reference conformal boundary condition to begin with, and then suppose that the boundary condition admits a set of exactly marginal boundary operators, which I denote as psi I. Then I can consider perturbing this relevant reference boundary condition by these marginal operators with some coupling constants alpha I. And this will map out some space of conformal boundary conditions near this reference boundary condition. I'm going to refer to this space of conformal boundary conditions as a boundary conformal manifold. And I'm going to denote them usually as M. And these marginal couplings alpha I, you should think of them as coordinates on this boundary conformal manifold M. Now, conformal boundaries appear in various different contexts. For instance, in condensed matter physics, they provide good models for impurities. For instance, famously, such as in Kondo effect. And in string theory, they provide the worship description of D-branes, which is very important. And in this context, conformal manifold of boundary conditions will naturally arise. For instance, when the impurity breaks a continuous global symmetry that's present in the bulk quantum system. In the context of string theory, this boundary conformal manifold will describe the moduli space of D-branes. They hold particular interest. And what do we already know about this such boundary conformal manifold? So just like the usual bulk conformal manifold, one can show that boundary conformal manifolds are also equipped with a Riemannian metric, again given by the two-point correlation functions of exactly marginal boundary operators. And before I get into the details, let me give out basically the summary of the talk. So what I'm going to try to do during this talk is to show you that beyond this usual Riemannian structure, we're going to find that boundary conformal manifolds come with some kind of higher geometric structure. I will try to explain what I mean by this higher geometric structure. In particular, we are going to introduce the notion of higher Berry connection and curvature on boundary conformal manifolds, and this will be based on OP coefficients of boundary condition changing operators, which I will explain soon. And our definition is inspired by similar quantities defined for families of invertible topological phases of matter, which is discussed in recent literature of quantum condensed matter physics, especially those based on tensor networks. So a priori, this is a very different subject from the space of conformal boundary conditions, it seems, but there is some connection, and I'll try to explain it. When appropriate, in the string theory context, it seems that our higher Berry connection is closely related to the Hart-Ramon B field in string theory. So this is the rough outline. So I'm going to first tell you what even is a higher Berry phase, and this intuitively. I'm going to briefly review the tensor network definition of higher Berry phase, in particular based on so-called matrix product states. And then I will tell you about the higher Berry phase on the conformal manifold of boundary conditions, and then I will summarize. And of course, feel free to interrupt with as many questions as you wish at any point. So what is higher Berry phase? So let me first remind you what is an ordinary Berry phase in quantum mechanics. So the context is as follows. So we have a family of quantum states, psi alpha, where this alpha is a collective notation for a set of n parameters, which is inside some parameter space M. And we consider a, say, family of Hamiltonians with this parameter, which depend on these parameters, and then the psi alpha is the set of ground states. And as we adiabatically tune the value of the parameters alpha, this ground state undergoes a time evolution, and under this time evolution requires some phase, geometric phase, which depends only on the trajectory gamma inside the parameter space M, where these parameters trace out. This is called the Berry phase. Berry phase is given by basically the holonomy of this one-form connection, or called Berry connection, along this trajectory gamma.
Is there any assumption there's a gap?
Yes, that's an important point indeed. So for this A to be well defined, we need to assume that for every value of alpha along this gamma, the Hamiltonian has a unique ground state, and there is no level crossing. And if there is a level crossing, this A will diverge. So this Berry connection, it's locally a differential one form inside the parameter space M. More precisely, it's a connection on the complex line bundle that is quantum states define. So in practice, how do we compute this Berry connection A? We can compute this by taking the inner product of two nearby ground states inside the parameter space, like so. So you take the inner product of the psi alpha with the psi alpha plus delta alpha, where delta alpha is a small variation from alpha. And at linear order, you find this connection A mu. Perhaps a more familiar expression will be the one in the bottom. This is the equivalent. And the point is that A can be computed by taking the inner product of two nearby quantum states. Then what is higher Berry phase? So higher Berry phase is a natural generalization of this quantum mechanical Berry phase for extended quantum systems with spatial locality. So this can mean, for instance, continuum quantum field theory, or it can also be quantum lattice models with short-range interactions. So what's important is that now you have a notion of space, as opposed to just having a time direction, as in quantum mechanics. So our focus will be on 1 plus 1 dimensional systems, so I have one space and one time direction. And when you have such a notion of spatial locality, what you can do is to adiabatically vary these parameters alpha, not just in the time direction, but also in the spatial direction. So the situation will be something like this. So I again have a family of states psi alpha labeled by these parameters. And similar to before, there needs to be some assumption about the uniqueness of this ground state. But with that assumption, I can consider have some QFT defined on a circle with coordinate x, which is 2 pi periodic. And now I slowly vary the parameter alpha, both in the time direction and also in the spatial direction. So this variation of parameter alpha will now sweep out a two-dimensional surface inside the parameter space, which I denote as sigma. Now you can ask, under such a time evolution from time t1 to t2, what happens to our quantum state?
So there can be a level of tracing, right? Just not on the curve itself that you're tracing it up. It's like somewhere else in my parameter space that could happen.
That's correct, yeah. So level crossing is allowed away from this sigma, but as long as on sigma there is no level crossing, it will be okay. Yeah, in fact, sometimes that's important because in some cases we can actually detect level crossing, where level crossing may happen by computing Berry curvature away from the level crossing. Thanks for that, Lisa. So. Okay, so we asked what happens to the quantum state when you go such a adiabatic evolution. So it's hard to make a rigorous hard to give a rigorous answer, but one may expect, one may speculate, perhaps there is an analog of geometric phase as in quantum mechanics, which depends only on the shape of sigma, but not on the details of time evolution. And this quantity is perhaps again given by the holonomy of now a two-form connection B along this sigma. So this will be a natural guess that one may have. And in this context, this holonomy of B along this surface sigma will be called higher Bary phase. And this connection B, which is now a two-form inside the parameter space, will be referred to as a higher Bary connection.
And the story works analogously for everyday number of spatial dimensions?
Yeah, exactly. So that's the expectation. So whenever we have a family of unique depth ground states in, say, D-dimensional QFT, we expect there to be a, say, D-form connection.
Yeah, the question for just 1 plus 1 dimension, I'm a little bit confused. So I followed the story in quantum mechanics where for every parameter, say alpha, you could find the ground state of the Hamiltonian,
Yes, yes.
and then imagine the parameters change in time,
Yes.
right? So the ground state does too. But here, I mean, in 1 plus 1 dimensions, I usually think of the Hamiltonian as a spatial integral,
Yes.
right? And then for that spatial integral, there is a ground state wave function.
Yes.
So how should I think of the wave function itself, or the parameter itself, as depending on space location?
Yes. So for instance, will be a good example. So alpha is some parameter in the Hamiltonian, some coupling constant in the Hamiltonian. So for constant alpha, I get the Hamiltonian, as you said, by integrating the Hamiltonian density along space. Now, when I do this integral, I'm also allowed to make alpha x dependent. So that gives some different Hamiltonian. So that's what I mean here. Similar to, say,
So alpha could be some like background magnetic field, and then in
Yeah,
that
exactly,
space you
exactly.
find the wave function.
exactly. So you can think of it as, say, in that case, like inhomogeneous and time-dependent background
Okay.
magnetic field, for instance. Yes, indeed. Okay. Any other questions? Okay. So the previous picture was just some intuition, but in general, it can be challenging to formalize this intuitive idea and to precisely define the higher Bary connection, B mu nu, and the associated curvature, H mu nu rho. And depending on the context, for instance, depending on whether we are interested in continuum field series or we are interested in spin chains and so on, there can be different definitions. And in fact, in the literature, various different approaches have been taken. And the one approach that will be most relevant for us will be the one that's based on what's called triple inner product or matrix product states. And I'm going to review what it is briefly, but these matrix product states are examples of tensor network states. And the idea is sort of simple. So just like the ordinary Bary connection, which can be obtained from the inner product of two nearby quantum wave functions, the main idea is to define higher Bary connection by computing the triple inner product of three nearby many-body wave functions represented by represented as matrix product states.
And this is specific to 1 plus 1. If you go to even higher dimension, we higher inner product.
Exactly, that's correct. So this is very particular to 1 plus 1D, and 2 plus 1D, we need to take the quadruple inner product.
Can you explain what phase if you do the naive thing of just taking the ground state at alpha and alpha plus delta alpha? Like the standard Bary phase, but now with delta alpha being space dependent as well. What phase?
Good point. So this is a subtle question, so one can try to define a usual Bary connection, but one problem is that generally in this context of, say, many-body physics, you want to define the thermodynamic limit. So you want to take the limit where the number of spins goes to infinity, and then the naive definition of Berry connection will diverge in this limit. Then you need to consider something like Berry connection per unit cell. Perhaps that can be defined, but yeah, but indeed it's not clear. So for instance, if you do that, then some nice properties like the quantization of Berry flux, things like this may not hold.
Well, I
Also,
guess
if you
consider
define it
the-
as this, how can you, probably you cannot get an antisymmetric form.
Yeah, you don't get, you just get a single gauge invariance, not two gauge invariance.
You
because
get if you take two derivatives, they commute on the wave function. I mean, one way to define the Berry phase is the
Yeah,
derivative of psi.
yeah.
So that will give you symmetric form.
But I think also you don't, I think you just get an mu in general more physical, because the gauge invariance is just the phase acting on the state globally, not modulated in space. What you want.
Yes. So
Okay.
yeah. So it seems not. Yeah. Yeah.
Okay.
I guess we are trying to take advantage of the locality, and
Yeah,
since
yeah.
two form is for network. Great. So okay. So let me briefly review how to define higher Berry phase in the context of tensor network. So not all the details of the tensor network side will be important, because our main focus is in any case on conformal boundary conditions, which I will get back to very soon. But anyways, in case not everyone is familiar with this, let me just briefly tell you what's the setup. So we're going to use so-called matrix product state. Here I denoted as psi alpha. Graphically, it's commonly denoted by a picture, something like this. So this is an example of a tensor network state, and why is it called a tensor network? Because so at its vertices here, I basically have tensors with three indices. There is an index corresponding to this vertical leg. This is called physical leg. It represents the physical hyperspace at this site. It can be, for instance, a qubit. So this index can be 0 or 1, for instance. Here I denote them as A1, A2, dot, dot, dot. And it has two more indices corresponding to this blue horizontal legs. These are called virtual legs. So they also carry some finite dimensional Hilbert space. So it's called a virtual Hilbert space. Let's say it's some d-dimensional Hilbert space. So then at each site, I basically have d times, say if I have a qubit here, then two tensors. If I fix this physical index to be some value A, then at each site I basically have d by d matrices A labeled by this local basis states. Now using these tensors, you can represent a quantum state, this thing called matrix product state, where you simply take the product of all these matrices at each site. And here I'm assuming I have a periodic chain, and that's why there is a trace here. And then you use that to as the coefficient for the your basis state A1, A2, L is the number of sites here. And the reason why these matrix product states are useful is because, for instance, if you think about it, the total dimension of the Hilbert space is 2 to the L if I have L qubits. And these matrix product states, they span some very small subspace of this large, exponentially large Hilbert space. But it is known in the literature that these matrix product states are good approximations to the gapped ground states of 1 plus 1D many-body Hamiltonians. And since we are mostly interested in ground states of gapped Hamiltonians, it seems sufficient to consider only matrix product states.
And sorry, what is the vector alpha 1, alpha 2, alpha L?
Yes, so these are, so I'm assuming at each site I have a single qubit, so this A1, A2, dot, dot, dot can be 0 or 1, all of them are 0 or 1.
And the A's are matrices acting only on the qubit.
So A's are matrices that, so they don't act on the qubit, they act on this blue leg, which is called the virtual Hilbert space. And these are basically just matrices labeled, some matrices labeled by 0 or 1.
But they act on A1, A2, I mean on the qubit space, right?
No.
No.
So
Tensors 3 indices.
They have 3 indices, right? They have index in the qubit space and matrices in some auxiliary space.
In some auxiliary space.
Some
that is-
auxiliary space, yes.
There, yeah.
Yeah. So for instance, if I wanna take the 0, 0 dot of the 0 component, then I just literally compute this product of these matrices A0, A0, dot 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 A0, and take the trace. Then there'll be the coefficient for 0, 0, 0.
So
in this
all
thing.
this trace is just a way of writing a linear combination of these states.
Exactly.
Between
Exactly.
states, which is
exactly. So
useful
this
for-
trace is taken in this auxiliary hyperspace. That's
And these indices, alpha, beta, they just correspond to different choices of capital A's, right?
That's correct. Yeah, sorry, I forgot to put it here. Yeah, so alpha is the label for the state. So here, this A is, maybe I could have put alpha here. Yes.
It has to be the same A, like same matrix.
Yeah, so more generally, so it depends on whether we want to preserve the translation symmetry or not. So it is okay to put different A's at different sites, but for the sake of this talk, I'm gonna always assume translation invariant. So yeah, I have the same A's at every site.
And when you say it's well approximated, presumably it depends on the number of the channelity of the auxiliary space,
That's
right?
correct. That's correct. So yeah, so the approximation gets better and better as we increase the dimension of the virtual hyperspace.
So that's what it means, well approximated.
Yes. Yes. So okay. So the crucial ingredient later will be the following. So consider that we are given two matrix product states, psi alpha and psi beta. So the important ingredient is the so-called mixed transform matrix. So graphically, this mixed transform matrix T alpha beta is can be drawn like this. So for instance, this blue represents the matrix product psi alpha. This orange line represents psi beta. I'm using dotted line because we need to take complex conjugation, but that's some technical detail. And this mixed transform matrix is obtained by first you multiply these two tensors, and then you sum over the physical index. So you glue the physical leg of these two tensors. And what's left is another tensor. It has 4 dangling legs. So it has D indexes here, D indices, D, so D to the 4 indices. I can group them. I can group these two sets of D number of indices as say 1 index. So and same for these two. And then what I want to say is that you can think of this basically as a D squared times D squared matrix. So it's some finite dimensional matrix at the end of the day. And then later we're going to make an assumption that this D squared times D squared dimensional matrix has a unique left and right eigenvectors with largest eigenvalues. And these will be called left and right fixed points, respectively. Here it's written as lambda left and lambda right. And so action of mixed transform matrix on, say, lambda left will be graphically drawn like so. Because it's an eigenvector, this action just disappears. And here I'm normalizing the eigenvalue to be 1. And same for lambda alpha. Lambda right. And so remember, our goal is to define the notion of triple inner product of matrix product states. And to do that, a crucial ingredient will be the following: star product and integration. For some people, this terminology may ring a bell or not. I'm not sure. But anyways, I'm going to explain later where this terminology came from. But anyways, star product is a way to multiply different matrix product states. So basically, you take two matrix product states, psi alpha and psi beta, and you divide both of them into two halves, left and right. And here, now, what you do is you glue the right half of the psi alpha with the left half of the psi beta like this. So you contract all these physical indices, and then it goes infinitely long. And then due to the assumption that, so here each part is simply the mixed transform matrix that we defined before. And then because of the assumption that it has the unique eigenvector with the largest eigenvalue, you can simply replace this part by insertion of this fixed point vector lambda, and it becomes like so. What is integration? Integration is basically, you can think of it as just taking the inner product of the psi alpha with this cell. And again, at the end of the day, it reduces to taking the trace of some fixed point vectors. Now, what is triple inner product? We take three matrix product states, psi alpha, beta, gamma. We take star products of all three of them. One thing to notice is that I didn't explain, but you can show that this star product is associated, so it doesn't matter which order you take this product. So here, for instance, I'm taking first product first, and then the second. And integration, you just close it left half with the right half, like this. So at the end of the day, when you do this triple inner product of three matrix product states, you are left with the trace of some finite dimensional matrix, which are these fixed point vectors, and it's some complex number. So it inputs three matrix product states and outputs some complex number.
Sorry, can you go back to the definition of psi alpha? That's
Yes.
something that I don't understand. There. So, are you summing over the alphas?
Yes, yes.
So why there is an index alpha in psi? I mean, shouldn't this be a dummy
Oh,
index?
sorry. This was yeah. So sorry. This is my. This is alpha and this is A.
Mm-hmm.
But I think Massimo is asking why there's, so on the right hand side, the alpha index are on A, capital A, and they're summed over in the trace, the bound indices.
Yes.
On the left hand side, you still have the alpha dangling index.
Yeah. What does it compose?
There's no alpha on the right.
This alpha.
Yeah.
Yeah. What is that alpha?
Yeah, sorry, I shouldn't have had. So alpha is so I used alpha and beta later to distinguish different matrix product states, meaning different A's, different tensors.
So the alphas really mean a collection of A. Right?
Yeah, yeah. So yeah. So I should have put alpha probably here.
The two equations, alpha mean different things.
Well, you could have called the A capital alpha, which unfortunately is A.
That's what you did.
Yeah, so sorry for my bad notation. So yeah. Okay. Any other questions?
Also about the notation, but on the other slide, so where you have the trace, is the trace just redundant? I mean, I think this, yeah. What's the meaning of it? I mean, here it's fine, because there's one more index, but the next, what is this trace?
Yeah, so it's the same. So trace is basically, when I have infinite MPS, I do it like this.
So by lambda itself, you do not mean literally just that tensor? Lambda R?
Here.
Yeah. I thought lambda has, so lambda is going to be a tensor of size d squared times d squared, capital lambda.
So
and you already got a
d
sphere.
by d.
Sorry?
D times d.
D by d.
Yes, yes.
Is there a meaningful distinction between lambda R and lambda L? Like, to
Yeah,
me,
yeah.
seems like
So
we
it's
relabeled.
because so this mixed transform matrix is generally not Hermitian, and yeah, because of that, the left and right eigenvectors may differ. Yeah, so that's the only reason.
Yeah, I think what I was just saying is that the trace was redundant. I mean, everything's already contracted between the lambdas. Because you were saying that alpha, beta, gamma takes value d in the, takes d values, right? They're labeling the.
So sorry, maybe my notation is confusing. So alpha, beta, gamma are labels for the matrix product states.
Oh.
It's not the it's not the index for. Okay.
Yeah.
So
Yeah, because at some point you were saying that this t, when you said about t alpha beta, you were saying okay, it takes value d squared.
Oh yeah, sorry, I did say that. So what I meant is this. Okay, so alpha and beta are some fixed
Yeah.
It's some fixed
The
label.
color. They're labeling the color.
They are labels for the color. So I don't vary them. So this entire thing is discrete times discrete metrics. And I didn't write the metrics indexes in this. That's right. Sorry, that was that was confusing.
Yeah, so I was just wondering, how do we choose, how to break these things up into left and right components, and will like our definitions depend on, where we decide they overlap?
Yeah, good question. So you are asking how to choose the midpoint.
Yeah,
basically. So here I'm considering infinite matrix product states, so they are infinitely long.
Yeah.
Yeah. So where you code it is all the same.
Okay.
Okay.
And sorry, there? Why it is 2 right and 1 left, and not 2 left and 1 right? It will be the same?
So,
where in this definition there was a symmetry between?
Yeah, that's a good question. So.
I think if we looked at the dotted lines on the slide with the green, right?
Right.
Yeah.
Just like the blue is all not solid and the green is all dotted.
There's a conjugation on one, so it's antilinear in one.
So you can let me make slightly imprecise comment, which is that roughly speaking, so you see here I have alpha beta, beta gamma, then alpha gamma, not gamma alpha. So I'm breaking the cyclicity property. So maybe I will come back to this later. So later I'm gonna sort of compare this picture with the boundary condition changing operators, and then lambda right and lambda left, they correspond to say some boundary condition changing operator psi and psi dagger, for instance.
But is there a different triple product which would give 2 left and 1 right, or they're just?
Yeah, I guess.
What would be the conjugate?
Is it just the conjugation?
Yeah.
Yeah.
Okay. So finally, so now let's try to define the higher break connection. So we consider a family of matrix product states. Here, injective means it's a unique ground state of a gapped Hamiltonian, so no level crossing. Again, parameterized by this set of parameters inside parameter space M. Now, we can use this triple inner product to define the higher break connection B mu as follows. It's very similar to usual definition of Berry connection in quantum mechanics. I'm taking the inner product of basically 3 nearby matrix product states, or I'm taking this particular derivative and then anti-symmetrizing in these indices. And I should say this is not how it was defined in these papers, in these original papers. I'm slightly improvising. But this is the version that we are going to use in the context of boundary conformal field theory. So before moving on to boundary conformal field theory, let's just step back and ask, why is this tensor network discussion at all related to conformal boundary conditions? Among other things, MPSs, they, as I said, they represent gapped ground states of many-body Hamiltonians. On the other hand, CFTs, we usually use them to describe gapless critical points. However, there seem to be several relations between gapped states and conformal boundary states. I think one of the direct connections come from the paper by Cardy. Unfortunately, I'm not gonna review it so much, but there is a sense in which this conformal boundary states, in the Cardy sense, when properly regularized, they describe gapped ground states of the CFT Hamiltonian perturbed by some relevant deformation. Anyways, so this boundary condition sort of behaves like gapped states. And another hint that I'm gonna get inspiration from comes from the connection to open string field theory, which I find quite interesting. So what is open string field theory? So of course we are not gonna use all the detailed machinery of open string field theory, but we are gonna just use it to get some intuition or some inspiration. But just to let you know, so in one sentence, open string field theory is basically a machinery which takes as an input a worldsheet boundary conformal field theory and outputs some target space-time action which describes the fluctuations of open string degrees of freedom in a given closed string background. So this was the action for such open string field theory was, for instance, written down by Witten about 4 years ago. The action takes the following form. Here, A is the open string field. Intuitively, you can think of A as the functional of the open string field configuration. This Q is the BRST charge on the worldsheet. It's not going to play any role in our discussion. And crucially, to define this action properly, you need to define what you mean by the star, which is called star product, and this integral, which is called integration. And just say that this previous definitions for star product and integration, or the terminology, in fact, came from this open string field theory.
Is it a coincidence that this looks like a Chern-Simons theory?
It is not a coincidence, so it's basically looks like a Chern-Simons theory. In fact, I suppose there should be many relations, but in fact, for certain topological strings, you can show that. So you see this thing depends on your choice of the closed string background to begin with. So if you choose the closed string background to be some particular topological string, it actually reduces the Chern-Simons theory in some cases. This is interesting. So let's see how this star product and integration was defined in the open string field theory side. In fact, it's very similar to what we were doing in the tensor network side. So here you have two string fields U and V. These are open strings, and you again divide them into two halves. Now you glue the left half of U with right half of V, for instance. So it's basically the same thing that we were doing in the MPS side. On the MPS side, we define triple inner product like so, and you can do a similar thing in the open string field theory side. Here I'm missing the integration, but when you take the integration, you get a similar picture here. So somehow, what we do in MPS, it looks like some kind of discretized version of what we are supposed to do in string field theory. Anyways, after some work, you can show that this cubic interaction term in open string field theory, which is basically given by the triple inner product of this open string field A. At the end of the day, this cubic interaction term is determined by various 3-point correlation functions of boundary operators. There is a more precise thing that I can say, but at this point, I'll just say this. And what we are going to do now is to combine these various pieces of knowledge coming from tensor network, open string field theory, and we are going to go to boundary conformal manifold, and then finally define our higher break connection. By the way, how much time?
15 minutes.
Okay, so yeah, that's good. So, okay. So now let's finally move on to our main interest. Consider some fixed 1 + 1 DCFT or 2 DCFT of interest, which admits a continuous family of conformal boundary conditions in the sense we discussed before at the beginning. So they are related by exactly marginal boundary perturbations. So these boundary conditions B sub alpha are labeled by these parameters alpha inside this parameter space M for boundary conformal manifold. A crucial ingredient in our definition will be the so-called boundary condition changing operators. So consider a discontinuous jump in the boundary condition, say from B alpha to B beta, and at the discontinuity you need to insert some operator which carries some definite conformal scaling dimension, and denoted as psi alpha beta. In particular, we're going to use the boundary condition changing operator, or BCC operator in short, whose scaling dimension is the smallest. So we're going to use lightest BCC operators. So upon state operator correspondence, these BCC operators map to states inside the Hilbert space of the CFT with boundary condition B alpha imposed in at one end of the interval and B beta at the other end of the interval. And this psi alpha beta will map to the ground state, which we assume to be unique. And motivated by various previous discussions, we're going to try to use the 3-point correlation function of these BCC operators to define higher bay connection. So we're computing CFT correlation function, which looks like this. So a disk, and boundary of the disk is divided into 3 different regions: B alpha, B beta, B gamma, and I have insertion of this lightest BCC operator. Of course, this correlation function is uniquely fixed up to the overall OP coefficient, which I denote as C alpha beta gamma. Here G sub m is the G function of this family of boundary conformal manifold. This is our convention for normalization, but it's not going to be very important. Yes.
In the tensor states, the lambdas, are they fixed? Are there multiple lambdas we can pick?
That's a good question. So that's one of the assumptions. So we are so in general there can be some degeneracy, and here we are making assumption that for this given family of states we have unique lambdas.
Okay.
And on the boundary conformal field series side, we are making a similar assumption that all these psi are unique ground states in the intervertebral space.
So related to Peno's question, so in case there are degeneracies, is there a possibility of an abelian higher barrier connection?
Yeah, that's a great question. So it's not so clear because, for one thing, for one thing, there seems in mathematics there seems to be some obstruction to define
the higher
non-abelian George. Yes. Yeah. So it's not clear. Yeah. Interesting.
But for the conventional verification?
Yeah, for that has that version. It's one form connection.
When you have a degenerate ground state.
That's right.
You generically have U1.
Indeed. Okay, so now we are going to define a triple inner product of boundary conditions simply as this OP coefficient of 3 BCC operators. And borrowing the intuition from tensor network, or the slightly improvised version thereof, we're going to define higher bay connection B mu nu by following expression. So here I'm using a little bit of a fancy notation, but here this thing really means I take this OP coefficient, I take derivative with respect to say beta and gamma, anti-symmetrize, and set beta equals gamma equals alpha. That's how I compute this B mu nu. It's a very concrete definition. And then once we compute this B mu nu,
so the opposite leakage invariance is the one you expect by the1 transformation of the foundation operator?
Yeah, great. I will briefly comment on that in a few slides. Yes. So once we define this B mu nu, there is a associated 3-form curvature defined in the usual way. I'm going to call it H.
And here you sum over all so you take alpha equal beta equal gamma and you sum over all the alpha in the C.
No, so alpha labels a point inside the conformal manifold. And so I do not sum over it, and this B mu nu, it depends on alpha.
But all the 3 points are the same.
All the 3 points are the same, yes.
You take the derivative with respect to beta and gamma, and then you set beta and gamma.
Yes, exactly. Yes. That's what we do. Yes. So because of this, at the end of the day, this is a technical point, but to compute B mu nu, we don't actually need to know C alpha beta gamma exactly. We need to only know it for beta and gamma infinitesimally close to alpha. So that's what we need. And this is related to Gabriel's question. So I'll be brief, but this definition, in fact, has a little bit of an ambiguity, which is that the definition was based on this disk correlation function. And in defining these BCC operators, I have the freedom to redefine their overall phase vectors by arbitrary U1 vector. And in view of time, let me not get into too much details, but under certain assumptions, you can show that these phase rotations of BCC operators, in fact, translate to the usual gauge transformation of the two-form connection by some one-form gauge parameter lambda. So far, this definition was motivated by various intuitions, guesses, and so on. At this point, we do not know if whatever we have written down right now has any physical meaning or not. This could have been nothing. And what we are going to do is to try to explicitly compute this B mu nu in various examples. And we're going to just try to check that we get something that looks sensible. And we'll see what we mean by that in actual examples. So let's take an example. So consider an SE2 level K West-Jumino-Witten model based on the diagonal moduli invariant. And there are many boundary conditions that are known in this theory. The most famous ones are so-called Hardy's boundary states. So these are boundary conditions that preserve the diagonal of the left-moving and right-moving boundary SE2 global symmetries. And they are labeled by the SE2 spin J running from 0 to k over 2. K is the integral level. Now, you can take, for instance, the Hardy boundary condition corresponding to spin 0 here, B0, and act on this B0, the left-moving SE2 symmetry. Since the left-moving symmetry is explicitly broken by the boundary, by doing this, I obtain a family of conformal boundary conditions labeled by the group manifold SE2. So we have a boundary conformal manifold SE2, or equivalently a free sphere. Now, I take this example and I compute this OP coefficient and explicitly plug that into our definition of the higher braid connection and curvature. And we find that in this case, the higher braid curvature is given by the West-Jumino-Witten term and level K. And it seems like something meaningful. So this gives some preliminary check that our definition of the higher braid connection and curvature is doing something physically meaningful. And one observation is that the flux of this free-form across the entire conformal manifold seems to be always quantized. And later we see an example where this is violated. Yes.
So if you consider the other type of Motion invariance, like B-type Motion invariance, where you see the quantization change appropriately because the correspondence.
Yeah, that's an interesting question. So we haven't tried this in D-type Motion invariant. So that's that I'm not sure. Yeah, but we have a different example where this quantization is violated, and that seems to be crucially related to whether the conformal manifold is a smooth manifold or whether it is singular.
You're into D, so this H, this H is what?
It's a free form.
And the small H.
Small H is the SE2 field.
But that's normally valid in two-dimensional space, so you normally have to extend it to, when you do the Wissomino, you extend it to an extra dimension.
So H is the coordinate on the boundary conformal manifold.
Yes, the boundary conformal SE2. Okay.
Yes. Yeah.
Okay.
Yes.
So you write down the worksheet, you put back, and you write in terms of the
Okay, so another example we can consider is the Narain CFT, where we have collection of compact boson fields, X mu. And here we can consider the family of Dirichlet boundary conditions for these compact boson fields. And let's say I have n compact bosons, then this family of Dirichlet boundary conditions will form a conformal manifold, which is n-dimensional torus. And in this case, we find that at least in some choice of the gauge pixel, the higher Berry connection that we obtain simply coincides with the Karp-Raman B field B mu nu that enters into Lagrangian. There is something to be careful about, which is that so here B mu nu is flat. So by a local gauge transformation, inside any local patch, I can make B mu nu 0. So what you really need to compute is the global holonomy of this B mu nu across non-trivial 2 cycles. And unfortunately, our current formulation of higher Berry phase doesn't allow us to do this. We don't know how to do it yet. So this is something to be checked in the future. And let me briefly mention the final example. Consider a just free compact boson, single free compact boson, at radius which is integer. So this corresponds to integer times the self-door radius in my convention. And in this paper, it was studied that this in this theory, you can start from the Neumann boundary condition, and then deform it by following, say, cosine and sine potentials, plus the usual parallel derivative of x. And all these are exactly marginal boundary perturbations, and they give rise to a 3-dimensional boundary conformal manifold. And in a later work, it was shown that this boundary conformal manifold globally takes the form of a quotient of SU2 by the following Gn action. And one thing to notice in this example is that this Gn action has a fixed point, and after quotient, it introduces some orbifold singularity. So we computed the higher Berry curvature in this example, and we find that it's given by the SU2 level 1 West-German-Witten term, independent of the radius r. So what this tells us is that if we integrate this higher Berry curvature along the entire conformal manifold M, then we get a fractional number, which is 1 over n. So somehow the quantization of the Berry flux is violated in this example. And it seems to be related to the fact that there is a singularity in the boundary conformal manifold. With that, let me summarize. So we define the notion of higher Berry connection and curvature on boundary conformal manifolds of 1 plus 1D conformal field series. The definition was inspired by developments in condensed matter physics, especially the study of families of invertible topological phases within the framework of tensor network. So the Berry connection that we defined are explicitly computable in several examples, and they seem to be closely related to the B field in string theory. There are various future questions. I'll briefly go through them. So one immediate question one can ask is whether there is a similar, some higher Berry connection in the usual conformal manifold of Borg perturbations. It seems natural to guess that we should be able to define a three-form connection on conformal manifolds of 1 plus 1D or 2D CFTs. I'll not get into details, but we have some detailed guess which involves intersecting configurations of conformal interfaces, which however seems very difficult to compute in practice. Another question is related to the anomaly matching. So a simplest mechanism that a boundary conformal manifold can arise is by explicitly breaking a continuous global symmetry at the boundary. We make an observation that whenever this broken symmetry at the boundary has a non-trivial Hooft anomaly, it seems to give us non-trivial higher Berry curvature in the space of conformal boundary conditions that comes from this breaking. So there seems to be some anomaly matching required. But we want to have a better understanding. So in some examples, we saw that this Berry curvature, the flux of Berry curvature was a fractional number. And, for instance, in this free boson example. boundary conformal manifold in that example can actually be understood as coming from the breaking of a continuous non-invertible symmetry, although I didn't explain it that way. And one may wonder whether there is any relation between anomalies of these continuous non-invertible symmetries and this fractional valued higher very flux. One mathematical question is to understand the more global structure that is defined by this higher Berry curvature. So just like ordinary Berry connection is a connection on a vector bundle, this two-form connection should be viewed as a connection on something called bundle job. So our results suggest that boundary conformal manifold have the structure of a job, but we do not know how to extract all the axioms, including various global properties of a job in our formulation. Finally, now we know that whenever we have a boundary conformal manifold in 2D CFTs, this space M is equipped with the metric G mu nu, coming from the generalization metric, and it also has this B field B mu nu we just defined. And when you have such a space, it seems very natural to consider a nonlinear sigma model whose target space is M with this Lagrangian. And in a small number of examples we have considered so far, somehow this sigma model seems to be equivalent to the original bulk CFT, but possibly in a dual description, also possibly up to some discrete gauging or orbit work. At this point, it's not clear whether there is any general pattern, but if something like this is true in general, it suggests a very interesting idea that somehow some boundary correlation functions, you should remember this G mu nu, B mu nu, they are at the end of the day determined by some set of boundary correlation functions. And it suggests an idea that these boundary correlation functions may somehow contain enough data from which you can, in principle, recover the full bulk CFT. So something like this is true in rational conformal field theories and also in topological field theories, and it makes us wonder. Okay, with that, I thank your attention, and I'm happy to take any other questions.
Yeah, so you know, for usual Berry connections, we have like a notion of like a Chern number, which has like you know, significances for a theory. I was wondering if you know if there is a notion of like higher Chern number, or other topological constraints that you know, and if you could touch on you know what kind of significance they have on the theory.
That's a great question. So the the analog of Chern number is in this case is something called Dix-Meyer-Doady number. It's basically integral of h modulo some imprecision. Yeah. So here I guess so this thing is the analog of higher Chern number. And then I was trying to tell you that when we have a boundary conformal manifold which is globally smooth, it seems like this higher Chern number is always some quantized integer in this normalization. Yeah, but it seems that when we have some singularity inside this conformal manifold, it can also be a fractional number, so it's like fractional Chern number.
Yeah. It seems like this is related to like in gauge theory. For SUN mod C2, we have fractional instantons because it's Stiefel-Whitney class. Like it really seems like this is very related to that.
Yes, indeed.
Topologic.
Yeah, potentially, yes. So one thing I should maybe one can say is that more practically, so in general, at every point, so at a generic point in the boundary conformal manifold, to apply our formalism, we need to require that the boundary condition is simple or elementary, meaning that it's not a direct sum of other boundary conditions. But in this example, actually, this is violated along the singularity. And there is a one-dimensional locus of conical singularity. And along this locus, in fact, have a superposition of n Dirichlet boundary conditions. And it seems to be somehow related. Because it's sort of similar to Lebesgue, but not. Yeah, okay, anyways.
Just a quick question. So your definition of this this higher Berry curvature doesn't seem to rely too much on the fact that you have a bulk two-dimensional CFT.
That's correct. That's correct.
So it could apply to, for example, general line defects in higher dimensional CFT.
Yes. So that's correct.
So then the meaning of this is even more murky, right?
Yeah, exactly. So the way we wrote down the definition, in fact, we can use the line changing operators.
That's right.
I guess one reason we didn't do it is, as you said, the connection to invertible states seems more clear. But we didn't try any example, so there could be something.
It could be interesting.
Yeah, there could be something interesting. Yeah.
Couldn't you have done the same, or use the same definition for bulk operators, bulk deformation? You can compute a 3-point,
Yes.
for instance, using the formulas of closed string field theory.
Yeah. Okay. So there are two approaches. One approach is, so here for boundaries we use the boundary condition changing operator. So the analog of that for the bulk deformation will be actually a conformal interface, where I deform the theory by the marginal perturbation on Hooft space. So that will give some conformal interfaces. So we think by computing some correlation function of these conformal interfaces, we might be able to define similar thing in the usual bulk conformal method. Another idea is indeed to use closed string field theory. So this is, and I think that these two might be actually related.
I think naively we'll want to consider this junction between conformal interfaces.
Yeah. So
which is kind of building the transition function from the geometric perspective.
Yeah, exactly. So that's basically our guess. So we want to have this, this intersecting shape which comes to, this 16 symbol. And that's the guess.
But even more simply, I mean, the first thing that will come to mind is to take, by state operator correspondence, 3 operators at 3 points on the sphere, and do the same computation here. You may take 1 or 2 or 3, and the family of operators.
But how is that related to the?
I mean, if you just want to define a Berry phase, right?
Yeah.
It's
not clear whether this is going to be non-zero.
Yeah, so the question is it non-zero? Is it
Sounds
not
like
pure
zero.
gauge?
Yes.
We thank Yichul again.
Thank you.